Hello everybody. So in this video we're going to discuss some special cases of the linear momentum equation that are going to be easier to deal with, and just to give a quick reminder that this equation that we are looking at here is the general form of the linear momentum equation. It's valid for steady and unsteady states, for uniform and non-uniform flows, for the constant and variable control volumes. That's why it's not easy to deal with integrations and differentiations, so it's not easy to deal with. So the special cases would be more easier to deal with, and this is what we're going to go through. But before we go through the special cases, I think it's important to quickly revise the physical meaning of these terms. So this term is the summation of forces acting on the control volume. This is the time rate of change of the momentum, and this is the difference between the momentum out and the momentum in. So we have the first case, which is the steady and uniform flow. So when we say steady flow, it means that there is no change with time. That's why the time dependence term is going to be zero, and this is the only term, which is the momentum out minus momentum in. So this is for steady flow. When we say uniform flow, it's something that we mentioned before. The velocity has a profile through the diameter of the pipe, or through whatever the channel it's going in or flowing through. So when we say that it's a uniform flow, we say that the velocity is almost equal to the average velocity. It's not it's not going to be exactly the same, but it's going to be very, very close. So if it's a uniform flow, then the velocity can be considered as constant, which is the average velocity. So if we have, so these are two things that will simplify the equation even more. The first is steady flow and the uniform flow. And if it's an incompressible fluid or flow, as we said before, we can consider that the density is constant, and we can recall back what we covered in chapter 5 when we were discussing the continuity equation, and we said that it's more convenient to express the continuity equation as rho u average times AC of the area, instead of having this integral form, because it's more easier to deal with. So if we combine this, if you compare these two, you'd see that this equation is very, very similar to this. The control surface is the area, so it's the same, but there is one more velocity that is multiplied here. That's why you can we can take or express this equation as this form. Rho u average times AC times u average as well. So of course the multiplication of these two is going to be scalar. That's why we have one vector out here. These three are the same as these three, so we can consider this as the mass flow rate times the average velocity. So the uniform flow is not always valid assumption, but it's reasonable if we have rounded entrances and outlets of the pipes, and for some types of flow, this is a valid assumption. So the equation will then be the an algebraic equation. It's not a differential equation as before, and it can be written as the summation of forces equals the summation of the m times the velocity average out minus the summation of momentum in, which is m u average in. Now there is one thing that is very similar to what we mentioned before in the Bernoulli equation, in the modified Bernoulli equation. It has to do with the velocity as well. And if you look at this equation here, you'd see that the mass flow rate contains the average velocity term, and it's already multiplied by the average velocity here as well. So it has average velocity power 2. It's rho a times the average velocity power 2. So and we said before that the assumption of steady flow is not always a valid assumption, or it's not very accurate assumption. So we need to so the momentum that we are calculating from here is not the same as the momentum we calculate from here. There is some deviation, and that's why we need to account for this using a correction factor. That's why we call it the momentum flux correction factor. We give it a symbol beta. It's the same thing that we did for the kinetic energy correction factor. So the equation can be written as, of course, this is the general form if it's unsteady, with what we can consider as a uniform flow. Okay, so in this case we can write the equation this way. It's still the time dependence term, but this is the beta here and the beta here. So if we have uniform flow, beta is equal to 1 because the actual and the average momentums are the same, and then we can write this equation, or this term, which is sigma beta mu average out minus sigma beta mu average in, is exactly the same thing. It's this. Okay, so it's another way of writing the equation. And if we want to get the form for beta, or get the value of beta, we can get it by integration, as we did before in the kinetic energy correction factor. So it's going to be the ratio of the actual momentum over the average momentum. So this is what you can, and as I told you, this is the U average square. This is what causes the big error or the big deviation. So this equation can be written in this form. It's 1 over area times the integral of U over U average per 2 times the AC. So it depends. If we know the formula for the average velocity, we'll just apply it on the formula here, and we can get beta. And this is what we can do here. This is a case of a laminar flow where the U is can be related to the average velocity in this way. So U equals 2U average times 1 minus r over r, r square over r square. The r is any radius, and the uppercase R is the maximum radius of the pipe. So if we want to get the momentum flux correction factor, we'll just apply the formula. So it's 1 over AC times the integral of U over U average per 2 times the AC. We already have the velocity here, so we'll just plug this formula in here, and this is what we have here. So we have U average square and U average square here. They will cancel each other, and with some math we know that the area of the circle is pi r square. So the d area is 2 pi r dr. It's just an integral 2 pi r dr. So this is why we have this as the dAc. And by doing math and applying the limits of integration and doing all this mathematical work, this is the correction factor we're going to get, which is 1.33. If it's a turbulent flow, we can get a much smaller value. That's why the turbulent flow is more closer to the assumption of uniform flow than the laminar flow. And again, we'll go through this in details in chapter 8 when we go to this point. Now we can have even more simplified equation if we have steady non-uniform flow. If it's steady, okay, then the time dependence term is 0, and the non-uniform flow is accounted for using the beta term. But if and this is the equation if we have more than one inlet and one outlet. It's all the outlets, the sum of the momentum of all the outlet streams minus the momentum of the inlet streams. But if we have one inlet and one outlet, it's going to be even easier. So it's going to be beta 2 m2 mu2, which is the outlet stream, and this is the same for the inlet stream. And keep in mind that all these equations are vectors, so it has 3 components in x, y, and z directions. So it's important to keep this in mind. And if we look again at this equation, if it's a steady flow, so there is no accumulation. If there is one inlet and one outlet, then the continuity equation will tell us that the mass in and mass out are equal, because there is like in this case you have only one stream in, one stream out, then the mass flow rate of the inlet stream and outlet stream are equal. it's a steady flow, so there is no accumulation. So we can take the mass flow rate as a common factor, which is mass flow rate multiplied by beta 2 U2 minus beta 1 U1. So we can write it in specific directions, like in the x direction, and the same for y and z directions. So this is the second case, and by the way, this is the case that we are going to be dealing with in most of the problems. It's either this or more than one inlet or more than one outlet, but at the end of the day, it's the same equation. The third case is kind of a case that is not of interest for us, at least for chemical and petroleum engineers, but it's an interesting case. We agreed that all the calculations that we do are on the surface of Earth, so we always have gravity, we always have forces acting on bodies, and so on. But there is a case where there is no external forces. If there is no external forces, it means that there is no weight, there is no pressure, there is no reaction forces, and this is going to be only for bodies in space. So if we have something in space, then the summation of forces is zero, and we still have the time rate of change of the momentum, and the momentum out minus momentum in. So the equation is going to be in this form. And this equation is the one expression of the conservation of momentums, and it says that if there is no external forces, then the rate of change of momentum is equal to the difference between the rate of incoming and outgoing momentum flow rate. So it's like the same thing we do for the conservation of mass. It's the accumulation of mass is mass in minus mass out. And if we cancel the velocities for these three, it's back to the conservation of mass principle. But anyways, if the mass is constant, then we can get the mass out of the integration of the differentiation, and it's going to be the derivative of velocity, which is the acceleration. So this is the mass of the control volume times the acceleration, and it's equal to the sum of momentum in minus sum of momentum out, which is called thrust, because this is what pushes the bodies in space. It's like the fire that comes out of the engine of a spacecraft or a rocket or something. So these are the three cases. Inshallah, next time we're going to start with solving some problems and applying the concept on some problems to get more understanding of this concept. So I'll see you next time, inshallah. Goodbye.